at 37 minutes, 11 Universal Time, as a billion-ton cloud of solar plasma was still pressing into Earth's magnetic field. The crust beneath the southern Philippines ruptured. In that moment, the strongest earthquake recorded so far in 2026 began, magnitude 7.8, arriving on the very day a strong solar storm had been forecast, and just 2 days after a moderate storm had already reached us. The timing is what makes the scene feel so uneasy. The stream of solar particles reached its peak the day before the Earth gave way, matching the kind of delay that some researchers have suggested could precede a major quake. So tonight, we place two restless systems beside one another, the sun above, the seafloor below. Was this simply a striking overlap, or could the planet have been responding in some subtle way to the sky? If that question is what brought you here, take a moment to follow calm space. Because these are the borderlands we return to again and again, where space weather and Earth's deep machinery appear, at least for a moment, to share the same stage. Tell us where you are watching from, and whether you felt this earthquake or saw the auroras that came with this storm. The data is where the story becomes more careful and more interesting. Let us begin with the first chapter, the strongest shock of the year. At 37 minutes 11 Universal Time, the ground beneath the southern Philippines stopped behaving like ground for roughly 60 to 90 seconds. Under Mindanao, the island floor rose, rolled, and buckled in a way no human body is designed to endure. People were knocked down. Swimming pools spilled their water. Building panels were torn away. By the time the shaking ended, the event had already entered the records as the most powerful earthquake detected anywhere on Earth so far in 2026, a magnitude 7.8. Yet the first unsettling detail is not only its strength, it is the day on which it happened. The quake struck while the sun itself was in an active, storming state. From the beginning, it is important to be clear about what this story can and cannot say. We are not claiming that the sun reached across 93 million miles of space and directly shook the Philippines. The honest science does not support that as a proven conclusion. And a dramatic explanation is not useful if it collapses under scrutiny. But it would also be too easy, and perhaps too careless, to dismiss the timing with a shrug. What happened is striking enough to deserve a patient look. The question is not whether a simple answer has already been found. The question is whether this was only chance, the sort of overlap that must happen from time to time on a dynamic planet beneath a dynamic star, or whether the data may be hinting at a connection we have not yet demonstrated. Hold that uncertainty gently. We may not arrive at a clean verdict, but we can at least understand why the question refuses to disappear. The first measurements show just how unsettled those early minutes were. When a great earthquake begins, the instruments do not instantly deliver a final truth. They offer rapid, automated estimates built from incomplete data and pushed out within minutes. Those first numbers were high. Early solutions climbed to 8.1 and 8.2, and for a short time, people watching the seismic feeds were looking at figures that cross into what is often called a megaquake, with magnitude 8 as the informal threshold. That distinction matters, because a megaquake is not simply a slightly larger disaster. It belongs to another class of release. Then, as more seismometers around the world joined the picture and the rupture was better resolved, the estimate came down. The United States Geological Survey placed the earthquake at 7.8. Other international agencies clustered around that value, though not identically. Australia's network read it near 8. Germany's read it near 8.1. Indonesia's read it near 1360. From different angles, they were all describing the same essential event: an immense rupture. At first glance, 7.8 and 8.2 may not seem very different. They sit close together on the page, as if separated by only a small step. But earthquakes do not follow the kind of scale we use in ordinary life. This is not like comparing 80 degrees and 84 degrees, where the difference may feel modest. Earthquake magnitude is logarithmic, meaning that each step upward represents multiplication rather than simple addition. A small change in the written number can mean a large change in the waves, and an even larger change in the energy released. So the gap between 7.8 and 8.2 is not a minor detail. In terms of energy, it is roughly an order of magnitude. The figures may look like neighbors, but the forces behind them are far apart. When the early 8.2 estimate settled to 7.8, that was not a trivial adjustment. In a sense, it meant the planet had released less energy than the first alarms suggested. Still, not everyone accepted the revision that way. Some observers saw the lower final number and believed it had been deliberately downgraded, and that reaction becomes one of the more revealing parts of the entire episode. We will return to that thread because it shows how quickly fear and data can pull in different directions. But before the argument over numbers can mean anything, we need to remember what those numbers did on the ground. A magnitude is easy to read and easy to scroll past. The lived reality is something else. Imagine a fast food restaurant in the southern part of the country, not far from the epicenter. The kind of busy place filled on an ordinary day with families, children, and workers taking a break. In the footage that emerged, the building does not merely crack or lose a wall. It collapses inward, the whole structure folding down. Now picture a vehicle dealership, its glass and steel crushed out of shape. Picture a multi-story residential block, transformed into a mound of concrete and rebar. Picture a high-rise still upright, but damaged at its foundation. These images matter because they pull the event out of abstraction. They remind us that behind every decimal point is a landscape suddenly changed, and a question that becomes harder to treat as distant. When the sky is storming and the ground is breaking, how should we read the silence between them? There is a kind of fracture that does not simply look ugly on a wall. It tells engineers, almost at once, that a structure has crossed a line. They can inspect it, measure it, and still conclude that no one should ever live or work inside it again. At that point, demolition becomes a decision made deliberately, because the building can no longer be trusted to hold itself upright. Now, imagine a shopping mall during the rising violence of the shaking. Its outer side panels tearing away and dropping in broad sheets, while a man caught in the scene staggers so badly that even standing becomes impossible. Imagine, too, a swimming pool during the same event, not rippling softly as it might in a minor tremor, but being hammered end to end, the water hurled over the rim and across the deck until, in only moments, the pool is almost drained. That detail matters. It is easy to overlook, but to someone watching for the language of earthquakes, it says something very specific. In a small quake, pool water usually rocks, laps, and settles into a familiar back and forth motion. When a pool seems to empty itself in seconds, the motion is pointing towards something far greater. And the reason is not simply that a larger earthquake shakes harder, though it often does. What grows with size is also time. A magnitude 5 1/2 or a magnitude 6 may give people perhaps 5, 10, or 15 seconds of motion at the upper end, a sharp strike, then silence. Mindanao endured something much longer, long enough for water to be thrown away as if the pool had rejected it, long enough for people in the recordings to lose the basic options of standing or running, and be reduced to gripping whatever was nearest while waiting for the ground to stop behaving like ground. Duration is one of the quiet signatures of a great rupture. The larger the break, the more time the fault needs to unzip, and the longer the surface continues to move. Here, that duration was harsh, and the consequences extended beyond the visible collapse of walls and roofs. A more hidden disturbance moved through the systems people normally depend on without noticing them. In Sarangani province, the electrical grid disconnected itself automatically. That was not random failure. It was a protective reflex built into the system. Faced with violent ground motion, the The grid opened its breakers to prevent parts of the infrastructure from destroying themselves. Transformers and substations went dark rather than risk catastrophic damage. Yet the protection came with a human cost: darkness, delays in telecommunications, and a region suddenly trying to reach loved ones at exactly the moment when communication mattered most. Operations at General Santos Airport were suspended, and one detail captures the force with an almost eerie symmetry. Inside the Philippines, one seismic monitoring station, an instrument built for the very purpose of recording earthquakes, was knocked offline by the largest aftershock. It is worth sitting with that image for a moment. The machine assigned to witness the shaking could not endure it. The observer itself was displaced, but the place where this happened also deserves to be held clearly in mind, because disaster footage can become strangely unreal when it arrives through a screen. The southern Philippines is not a diagram, not a headline, and not a statistic. It is a living region of millions of people, with cities, towns, villages, markets, schools, churches, and familiar restaurants where ordinary afternoons unfold. When that fast food restaurant collapsed, it did not fall onto an abstraction. It came down where people had been doing the most human things imaginable: eating, speaking, waiting, living. That is why the human scale has to remain beside the geological one. The physics matters because people are caught inside its consequences. A fault has no interest in the magnitude scale. That scale is something humans created so we can give shape to what has happened to us. So as we move tonight into the science, into trenches, flux, and the strange question of the sun, we should keep one part of our attention fixed on the reality beneath the analysis. This was, before anything else and after everything else, a human event, and somewhere families were searching through rubble for people they loved. All the mystery, all the speculation, and all the wonder rest on top of that. That is the ground of the story. What failed, how violently it failed, and what it began to cost. The complete casualty picture will come later, and it needs to be treated honestly, because the honest version of any disaster is often more difficult than the first version people hear on the first day. For now, hold two things together. The blunt fact of the strongest earthquake of the year, and the strange timing of the sun 93 million miles away, sending storm after storm across the space between us. 2 days before this rupture, a geomagnetic storm had already reached Earth and disturbed our magnetic field. Within hours of the quake, a stronger one was expected to arrive. On the same day, in very different ways, the planet and the star both seemed to be in motion, and almost no one was placing those events side by side. Calm space will do that carefully. Was it coincidence? It may have been. It very probably was. That needs to be said plainly at the beginning, because the question should not be allowed to outrun the evidence. Before we can even ask whether anything in the sky had any relationship to the seafloor, we have to understand the break itself. The exact style of motion deep beneath the ocean floor is the first useful clue. It also helps explain why. On a day when a magnitude 7.88 earthquake struck near a coastline, one feared disaster did not unfold in the way many people expected. Part 2 begins there. What a reverse thrust really is. Earth's crust has only a few basic ways to fail, but the differences between them can decide whether a coastline is drowned or merely shattered. So this one has to be approached slowly. The southern Philippines did not experience only a large earthquake. It experienced a particular kind of large earthquake. And that detail is central to one of the most important questions of the event. Why the tsunami many feared, the wave that seemed as if it should follow, largely did not. This was a reverse thrust earthquake. The phrase can sound cold and technical, but the motion behind it is physical enough to imagine with your own hands. Place your hands flat in the air, one hovering above the other, palms facing down, as if they were two heavy plates of stone stacked in the dark. Now picture pressure closing in from the sides, not gently, but with a vast and patient force, squeezing those layers until the system can no longer hold its shape. In a reverse thrust earthquake, the failure is not a sideways scrape like the well-known faults of California, where blocks of crust grind past one another horizontally. Instead, one mass of rock is driven upward, climbing over the other in a sudden vertical surge. For years, perhaps for centuries, the crust stores that strain in silence. Then, in a brief release, one block is pushed toward the surface. It is a simple motion to imagine, but a profound one to measure. To see that motion clearly, scientists turn to waveform data and calculate what is known as a moment tensor solution. In plain terms, it is a mathematical portrait of the way the fault moved during the event. For this earthquake, the two possible solutions pointed to the same essential geometry. The fault plane dipped at about 45 degrees, neither flat nor upright, but set on a clean diagonal through the crust. Its movement was overwhelmingly compressional, up and over, with only a very slight sideways element, just the faintest suggestion of oblique slip. In the most direct sense, this was the crust yielding under pressure by lifting part of itself upward. That detail matters because, in the language of earthquakes and oceans, direction is never just direction. It can decide whether the sea merely stirs or rises with force. Then comes the quiet number that controls nearly everything that followed. It is not the magnitude, even though that is what most people notice first. It is the depth. The rupture occurred about 55 kilometers down, roughly 34 meters beneath the surface, within the subduction system off the southern coast of the Philippines. In tsunami science, that depth can separate a frightening alert from a coastal catastrophe. The difference may sound hidden, buried far below view, yet it governs how much of the earthquake's motion reaches the water above. A deep earthquake can be immense and still fail to deliver the sharp upward punch that the ocean needs in order to build a truly destructive wave. The birth of a tsunami has a particular recipe, and once that recipe is clear, the day's outcome becomes easier to understand. First, there must be reverse thrust motion, the kind that lifts the sea floor, but the lifting has to occur close to the seabed, in shallow crust, so that the rock's sudden rise is transmitted directly into the water column sitting above it. Imagine the ocean basin as the floor of an enormous, silent bathtub. If a shallow thrust fault snaps right beneath that floor, the seabed heaves upward in an instant, and the ocean above it is forced upward too. A temporary mound of water is created, but it cannot remain stacked in place. It spreads outward, collapsing into motion, racing across open water as a tsunami, a pulse of energy that can cross the sea with extraordinary speed. That is the dangerous arrangement. Shallow, abrupt, vertical movement right at the sea floor. At 55 kilometers down, however, the story changes. The upward motion begins far below, buried under layers of crust. By the time that movement is communicated toward the seabed, it has been distributed, broadened, and weakened. The ocean still registers the disturbance. The sea is not unaware of what happened below. But the concentrated upward shove that can build a lethal wave has been softened by all the rock between the rupture and the water. Even for a magnitude 7.8 event, depth can remove much of the tsunami's force. In this case, that buried origin appears to have acted like a buffer, not stopping the earthquake, but muting the ocean's response. That is essentially what forecasters around the Pacific watched unfold in real time. Immediately after the rupture, a tsunami advisory was issued. The concern then sharpened into a tsunami threat, and the projected wave heights looked serious enough to command attention. 1 to 3 m along parts of the Philippines, and roughly 1/3 of a meter to a meter for parts of Malaysia. The Gulf of Thailand was expected to receive little to nothing for several hours. The question remained alive and unsettling. Coastal communities had reason to watch the gauges, to wait for reports, and to wonder whether the deep sea was carrying something larger towards shore. Then the measurements arrived. and the outcome was merciful. The highest observed wave was on the order of 1.1 feet, about a third of a meter above the normal tide. After that, the threat was declared to have passed. A region that had every reason to prepare for water was met, in the end, by a shove rather than a flood. The deep hypocenter, that 55 kilometers figure, stands out as the central reason the event did not become a far darker coastal disaster. It is sobering to think that a single buried number, invisible to anyone on shore, may have shaped the difference between alarm and tragedy. Still, caution is important here, because a small tsunami is not the same thing as a harmless one. A tsunami is not like an ordinary beach wave, curling neatly and then withdrawing as if the shore were in control. It is better understood as a rise of the sea itself, a moving mass of water that pushes inland and continues to push with enormous momentum behind it. Even 1.5 feet of fast-moving tsunami water can knock an adult from their feet. Once someone falls in that flow, the danger changes completely. They are no longer simply standing in shallow water, but being carried by it. People can drown in tsunami water that, if still, would not even reach their knees. The risk lies in the speed and mass, not only in the visible height. That is why the small observed wave should be seen as genuine good fortune, not as proof that the danger was imaginary. The ocean's response was restrained, and that restraint hinged on a number most people would never think to ask about: 55 kilometers. Remember it, because in this event, that depth likely saved lives. The figure may sound technical, almost remote, but it belongs at the center of the story. It reminds us that the planet's most important details are often hidden far below the surface. Now consider the energy involved, because magnitude 7.8 is difficult to feel in human terms without comparison. The numbers are so large that they can become abstract, floating beyond imagination. A magnitude 7.8 earthquake releases something on the order of 7.12 million metric tons of TNT equivalent. If that scale still feels impossible to picture, place it beside something more familiar, though no less disturbing. It is roughly equal to 500 Hiroshimized bombs, 500 of them, released within about a minute beneath the ocean floor. Such a comparison does not make the energy easy to grasp, but it does begin to reveal the violence hidden inside a number on a seismic scale. Another way to frame it is against the largest nuclear weapon ever detonated by anyone, the enormous device tested by the Soviet Union in the early 1960s. This earthquake released about 1/10 of that energy. Set beside the Krakatoa eruption of 1883, it was around 3% of the energy of that event. An eruption so violent it was heard thousands of miles away and changed the color of sunsets around the globe for years. And within earthquake terms alone, the contrast is just as dramatic. This event released roughly 200 times the energy of a magnitude 6.5. That is the meaning hidden inside a small difference on the magnitude scale. It is not a gentle step upward. It is a leap across a vast gap. There is something almost vertiginous about pausing with that comparison. 500 Hiroshima bombs. Not because the earthquake was a bomb, but because the image helps the mind approach a scale it otherwise resists. Beneath the ocean floor, in stone and pressure and sudden release, energy moved through the planet on a level far beyond ordinary experience. And yet the coastline was spared the worst, not because the earthquake was small, but because its violence began deep enough to reach the sea in a diminished form. That is the strange mercy of this event. Immense power below, a muted wave above, and a single depth measurement quietly shaping the human outcome. I am not bringing up this comparison to make the moment feel more dramatic. I am bringing it up because it gives us a clearer, colder sense of the scale at work. Human beings often imagine our own technology as the peak of power on this planet. Our weapons, our engines, our towers, our machines. Yet, along one fault, in roughly a minute and a half, Earth can release an amount of energy comparable to hundreds of the most frightening devices we have ever built. And it does not do this as some once-in-history catastrophe. Somewhere on Earth, in one form or another, this kind of planetary maintenance happens in many years, as the crust slowly adjusts itself. The ground beneath us feels like the definition of stability, the thing we trust without thinking. But it is also one of the strongest natural systems we will ever live beside, and one of the least open to our control. That is why this point matters, for the question at the center of tonight's story. Once you appreciate the enormous energy stored inside a fault, it becomes easier to see why many scientists hesitate when someone suggests that a faint electromagnetic signal from the sun might be enough to set it off. The system supposedly being pushed is immense beyond ordinary intuition. The proposed push, by contrast, seems almost impossibly delicate. That imbalance sits at the heart of the scientific skepticism, and we will return to it later. For now, simply hold the contrast in mind. A soft solar nudge, and the vast, violent machinery it is being asked to move. It raises a quiet but important question about scale, and about how easily our minds can connect two events that may not belong together. So why, in a strange and uncomfortable sense, can we say the region was fortunate that this was only a 7.8? Because the southern Philippines is capable of producing earthquakes far beyond that. The recorded history of this area includes magnitude 8 events, even magnitude 8.5, across geological time. A magnitude 9 inches, a zone like this, cannot be dismissed. And a magnitude 9 is not merely a slightly worse version of today's earthquake. It carries dozens of times more energy. Every step upward in magnitude that did not happen here represents devastation that remained withheld. Energy that stayed trapped in the rock rather than entering streets, homes, and lives. This is not said to soften the tragedy. Buildings collapsed, people were killed, and families are mourning tonight. The point is accuracy. This quake sits on a spectrum, and that fault's upper end is far more severe. That spectrum matters because we are moving toward the hardest question of all, whether the timing was shaped only by the ordinary movement of tectonic plates, or whether something else could have played a role. We have to speak plainly about the human cost as well, because the more truthful account is often more difficult than the first reports. The United States Geological Survey runs an impact model that estimates possible casualties and damage by using the earthquake's size, depth, and location. For this event, that system issued an orange alert. It did not give one single outcome. It spread the risk across probability bands. There was something like a 40% chance that deaths would fall between 10 and 100. There was something like a 35% chance of a toll between 100 and 1,000. And there was even a single-digit percent chance, small but still real, that the number could rise above 1,000. Economic losses were estimated from the low hundreds of millions of dollars toward $1 billion and possibly beyond. Here is the part that people who have watched disasters unfold understand, and it needs no exaggeration to be sobering. The earliest numbers are usually too low, not because anyone must be concealing the truth. We will come back to that accusation, because it deserves care, but because the first hours are filled with blind spots. No one can instantly see inside every collapsed building. No one can immediately reach every cut-off town. No one can count the missing who have not yet been found. Over the next days, and sometimes over the next week, the numbers rise as debris is removed and the picture becomes less blurred. This pattern has appeared again and again. In a neighboring region, not long ago, a magnitude 7.7 was first associated with estimates of only a few dozen deaths, before the confirmed toll climbed into the hundreds and beyond. So when the first-day casualty figures appear, they should be handled carefully. Expecting them to change is not cynicism. It is simply the slow, grim way disaster becomes measurable. But an earthquake of this size does not behave like a single blow followed by silence. It strikes, and then the earth continues to answer, sometimes for weeks. In the hours that followed, what the ground did next opened an unsettling question, one that shadows every major earthquake at the beginning. Had the worst already passed for the Philippines, or was the most dangerous moment still waiting? Now we come to the aftershocks, and to the uneasy possibility of a foreshock. As soon as a great earthquake stops, another process begins, and that process can continue for weeks or even months. The main rupture has violently disturbed the surrounding crust. Stress that may have accumulated over centuries is suddenly redistributed, and the rock responds through aftershocks, a long, uneven chain of smaller quakes as the crust tries to settle into a new state. Each tremor is an adjustment, like the creak of a house after a heavy weight has slammed onto the floor. Within the first hours after the 7.8, the southern Philippines experienced at least 3 separate aftershocks of magnitude 6 or greater. The largest was first reported as a 6.4 and was later upgraded to a 6.5. That detail matters. A magnitude 6 earthquake by itself is not minor. In a populated place, during an ordinary week, it would be a major headline and a serious damaging event. It sounds smaller here, only because it followed something much larger, something that changed our sense of scale. The word aftershock can be misleadingly gentle, almost like an echo fading away in the distance, but that softness can hide the danger. When the main rupture ripped through the crust, it did not leave behind a neat, calm, stable block of rock. It left a broken and stressed region, fractured and unsettled, where the previous balance had been destroyed and a new one had not yet formed. Each aftershock is part of that search for balance, arriving one jolt at a time, and in towns where buildings have already been cracked or weakened by the first quake, an aftershock that might have been survivable on its own can become the final force that brings a damaged structure down. That is why the hours and days after a great earthquake remain so perilous. Rescuers working in rubble face continuing risk. People are warned away from damaged buildings for a reason. The disaster is not fully over when the first shaking stops. In some ways, the landscape is still deciding how it will settle. The first earthquake may seize attention, but the aftershocks often deepen the human cost. They return to buildings already weakened, to slopes already disturbed, to communities that have barely begun to understand what has happened. Seismology has a formal rule of thumb for this pattern, but the essential idea is simple enough. In a typical sequence, the largest aftershock is usually about 1 full magnitude smaller than the main shock. After a magnitude 7.8, that would suggest a strongest aftershock near magnitude 6.8. The timing has a rhythm as well. At the beginning, especially during the first hours, the smaller quakes arrive in dense clusters. Then, across the following days and weeks, their rate declines in a fairly regular mathematical way. For a 7.8 event, a broad expectation would be something like 5 or 6 magnitude 6 earthquakes over the full aftershock sequence, with the upper end possibly approaching that 6.8 level, followed by a long diminishing train of 5s, 4s, and 3s. As reports accumulated, the Philippines had already recorded several magnitude 6 aftershocks, with a 6.5 standing as the strongest so far. If that general rule continues to apply, the sequence may not yet have delivered its largest secondary shock, and one could still arrive slightly above what has already been measured. That possibility matters, because aftershocks are not random background noise. They are part of the same physical story written into the fault. The main shock is the dominant release, the instant when the largest locked section finally fails. Yet that rupture does not erase every surrounding stress. Smaller locked zones remain, and nearby fault segments that did not break during the first event can be pushed closer to failure by the very earthquake that just occurred. In rough terms, the largest of those remaining patches often has about 1/10 the area of the patch involved in the main rupture, and on the logarithmic magnitude scale, that difference corresponds to about 1 magnitude. So, the rule is not merely a statistical curiosity. It reflects the approximate geometry of stress, rupture, and release inside a fault system. There is an almost self-similar quality to it. A major fracture followed by a lesser fracture, then smaller ones after that. Each step echoing the last with less force. That knowledge does not make the shaking safe, and it cannot remove the fear from people living through it. But it does allow forecasters, often within minutes, to offer a realistic picture of what may still follow. In a crisis, even an imperfect expectation can become a form of shelter, because it gives people something steadier than dread to organize around. There is, however, another path this story can take, and it should be approached with care. This is the possibility people fear most, that an earthquake first labeled as the main shock later proves to have been only a foreshock, a preliminary tremor before a still larger rupture. It does happen. It is uncommon, but it is real, and it would be dishonest to pretend otherwise. For a magnitude 7.8 to be merely the beginning of a larger event, the probability is low, on the order of a few percent at most. Even within that concern, the observed pattern offers some reassurance. A strong aftershock sequence that gradually fades is usually the signature of a principal rupture releasing stored energy, not a system quietly gathering itself for a greater blow. In a metaphorical sense, the crust appears to be breathing out tension rather than holding it in. Still, a few percent is not the same as zero, and the historical record gives us examples that are hard to ignore. In 2023, Turkey experienced a magnitude 7.8 earthquake, followed only hours later by a magnitude 7.5, two devastating shocks on the same fractured fault system in rapid succession. Looking farther back through history, there are even rarer instances of paired megaquakes striking the same region close together, with the ground breaking twice in a time span that geology would normally stretch across centuries. These cases sit at the unlucky edge of the distribution. They are not the expected outcome. The far more likely scenario, the 95% and better case, is that the magnitude 7.8 was the main event, and that the magnitude 6 earthquakes are aftershocks that will diminish as the crust adjusts. Yet clear communication requires holding both truths at once. The larger disaster is unlikely, and it is not impossible. That is why the next few days call for attention without panic, and caution without the false promise that all danger has already passed. The most practical part of the aftershock story is not conjecture at all. It sits on some of the firmest ground earthquake science can offer. When a fault breaks, it does not simply empty its own stress and leave everything nearby unchanged. The rupture relieves pressure on the patch that failed, but that same motion shifts stress onto surrounding areas, adjacent faults, neighboring segments, and nearby structures that may now be carrying a little more load than before. This process is known as stress transfer. It is ordinary, well-documented earthquake physics, not a fringe idea or an alarmist interpretation. And the southern Philippines is not resting on a lone, isolated fracture. It lies within one of the planet's most intricate tectonic regions, where several subduction zones press against one another in a crowded and unstable arrangement. The Cotabato Trench is the structure this earthquake appears to have ruptured along the southern margin of the Philippines. To the east lies the Philippine Trench. To the north lies the Manila Trench. Both of those neighboring systems have also shown recent restlessness, with their own activity in recent months. A magnitude 7.8 on one part of this network is precisely the sort of event that can alter the balance of stress on nearby faults, adding a small but meaningful push to systems that were already accumulating strain. So the cautious, defensible expectation is not that the region immediately becomes quiet. It is that activity continues. More aftershocks from the main rupture and a short-term elevation of stress on the adjacent trenches that deserves close watching in the days ahead. The history of this particular region supports that concern. And it also brings us back to the larger question running beneath the entire sequence. Seen against the long record of the region, this earthquake, however devastating for the communities near it, does not need to be treated as something alien or bizarre. It happened in a part of the planet where violent motion is part of the geological script. The Cotabato Trench has already shown that it can generate enormous ruptures, including one near magnitude 8.3 inches, 1918, more than 100 years ago, and larger than today's event. Within a radius of 300 kilometers from the present epicenter, the historical catalogue contains roughly 35 earthquakes at magnitude 7 or above. That number is worth letting settle for a moment. 35 major events in the same broad neighborhood. In the southern Philippines, a magnitude 7 earthquake is not a once-in-many-generations surprise. In most years, the region produces one with the grim regularity of a recurring season. Even the months before this rupture now look different. Back in January of this year, 2026, an earthquake swarm shook this same stretch of the Cotabato Trench, ranging from small tremors to events around magnitude 5.2, strong enough that schools and government offices in the region had to close. At the time, the swarm was disturbing, but it did not necessarily point to catastrophe. With the present event behind us, however, it may resemble a long-range foreshock sequence on the same structure that has now broken. In quieter language, the fault may have been announcing strain before the main rupture arrived. Beneath all of this is a simple but relentless driver. The plates here converge at about 7.3 centimeters a year, among the faster rates of convergence on Earth. That helps explain why this corner of the world is so persistently active. The crust is being compressed, stress is accumulating, and the true uncertainty is not whether strain will build, but when it will be released, and how large the release will be. That figure, 7.3 centimeters a year, deserves a slower reading. To human ears, it sounds almost harmless, a movement so small that it feels less like danger than background. It is slower than the growth of fingernails, slower than the hair on a person's head. But geology does not measure time the way a life does. Over one human lifetime, that yearly motion adds up to several meters of displacement. Across the century, since that great 1818 earthquake, the total becomes many meters of accumulated movement. If the fault remains locked, that motion does not simply vanish. It is stored as strain, like a spring being tightened in silence. Year after year, no one can feel the loading directly, and yet the system continues to gather energy. Then, in perhaps 60 to 90 seconds, the stored strain is released. That is the terrible nature of a great earthquake, a long interval of almost invisible preparation discharged in a minute and a half of destruction. The contrast is what makes these zones so dangerous. The loading is slow enough to escape human perception, while the release is sudden enough that no one can outrun it. This is the brutal arithmetic of plate boundaries, and it may be the hardest part for the mind to hold. The disaster seems instant, but the conditions behind it have been forming for generations. So, the geological story, taken on its own, is not mysterious. That is important because it sharpens the strangeness of what comes next. The mechanism fits the textbooks. The depth helping to reduce the tsunami threat fits the textbooks. Aftershock decay, stress transfer, and the regional background rate all sit comfortably inside ordinary seismology. Nothing about the earthquake itself, if considered only as a rupture on a known fault, requires an exotic explanation. A familiar fault in a familiar collision zone failed in a familiar way, broadly consistent with its own long and violent past. If a seismologist were handed the data without the date attached, the likely reaction would be calm recognition. The Cotabato Trench had behaved like the Cotabato Trench. And that is precisely why the timing becomes so compelling. This was a textbook earthquake, one that did not need any unusual cause. Yet it arrived on the very day when the sun seemed to be unleashing an extraordinary amount of activity toward Earth. The ground was doing something ordinary for that region, while the sky was having a far less ordinary day. To understand why that coincidence made so many people pause, we have to lift our attention from the fault and look outward. Part 4 begins with a different source of disturbance: what the sun had been doing. In the days before the earthquake, our star had not been quiet. The timing drew attention because the sun had just passed through one of its more active stretches in some time, and much of that activity appeared to come from one troubled area on its visible surface. It was essentially a single active region complex, a magnetically tangled neighborhood of sunspots, building itself into a state of agitation. The sequence began with flares. On the 3rd of June, that active region complex produced a rapid series of eruptions. First, a magnitude 9.3 flare and a magnitude 7.7 flare within roughly a 10-hour span. Both were powerful M-class events, belonging to the second strongest category of solar flares. Later on that same day, the region intensified again and reached X-class, the highest category, with a flare around X10. That escalation matters because flare classes are not a gentle, even scale. Like earthquake magnitudes, they jump by large factors, with each letter representing roughly 10 times the energy of the class below. Class flares are minor. M-class flares are moderate to strong and can interfere with radio. X-class flares sit at the top, associated with the most serious potential effect. For a single region to produce an M9, an M7, and then an X flare within one day is a striking performance. In Earth terms, it is a little like watching a fault zone rupture, settle, and then rupture again, as though the system has not yet finished expressing its stress. The comparison is only a framing device, but it helps convey the impression this solar region was unusually restless. A flare, though, has a specific role, and it is important not to give it more power than it has. A solar flare is a burst of radiation, light, X-rays, and ultraviolet emission crossing space at the speed of light. It reaches Earth in about 8 minutes, the same travel time as ordinary sunlight. When a strong flare arrives, it can disturb the upper atmosphere and degrade or even black out radio communication on the daylight side of the planet within minutes. That effect is real, and it can matter for aviation and emergency communications. But for this story, the distinction is crucial. A flare is not the solar component that would be expected to reach down and interact directly with the solid Earth. Its radiation flash affects the high atmosphere and then passes. If we are looking for the part of solar activity that travels more slowly, carries more mass, and could at least raise questions about interaction with Earth as a system, we have to look to a different kind of eruption. That heavier solar material came on the 6th of June, when the sun launched a coronal mass ejection. Picture the event not as a neat scientific label, but as something vast and physical. A coronal mass ejection is a traveling cloud of magnetized plasma, an immense surge of electrically charged particles held within its own magnetic structure, torn away from the sun and thrown into interplanetary space. This is not sunlight racing quietly across the void. It is material roughly 1 billion tons of solar substance, moving outward across the 93 million miles between the sun and Earth, like a world-sized projectile released into the planetary neighborhood. In this case, the cloud was linked to a filament eruption on the sun, a huge arch of plasma breaking free from the solar surface. Its early speed estimate came from a Type 2 radio sweep, the radio trace left by a shock wave forcing its way through the solar atmosphere almost like a plasma sonic boom translated into radio sound. That signal suggested a velocity near 838 kilometers per second. Pause with that number for a moment. 838 kilometers every second, moving with enormous force, and at least partly directed toward us. Holding that image in mind helps correct a quiet misconception. Space between Earth and the Sun can feel, in imagination, like a sterile emptiness, a clean vacuum separating two distant bodies. Yet the region is threaded by the solar wind, a continuous outward flow of charged particles, and through that moving medium the Sun can launch these gigantic clouds. Earth is inside this environment, not outside it, immersed in the Sun's extended influence, connected by magnetic field lines and particle streams, close enough to register solar disturbances. Once that becomes intuitive, the idea that the Sun affects Earth no longer sounds strange. It does so continually, in many measured ways. The unresolved question is narrower and more delicate, whether that connection could, in some still unproven manner, reach down into solid rock and the faults hidden within it. Now add the geomagnetic storms, because here the timing becomes difficult to ignore, even if coincidence remains possible. A geomagnetic storm begins when a solar cloud, or a faster stream within the solar wind, strikes Earth's magnetic field and disturbs it, making the planet's protective magnetic bubble shudder and resonate. These storms are classified from G1, meaning minor, through G2, moderate, G3, strong, G4, severe, and finally G5, extreme. 2 days before the earthquake, on the 5th of June, Earth had already experienced a G2 geomagnetic storm. The Planetary Activity Index, the number used to describe the level of magnetic disturbance, reached about 6.3. In a real physical sense, the Sun had just shaken Earth's magnetic field, setting it vibrating like a bell. Then came the forecast for the 8th of June, the day the earthquake occurred in local time. Official forecasters at the Space Weather Prediction Center issued a formal watch, not for a minor disturbance, but for a G3 strong geomagnetic storm expected from the arrival of the 6th of June cloud. The activity index was forecast to reach roughly 6 2/3 during the afternoon hours in universal time. So the earthquake was not merely near some vague interval of heightened solar behavior. It fell between two specifically identified geomagnetic events, a moderate storm 2 days earlier and a strong storm anticipated for the same day. That does not prove a connection, but it sharpens the question and gives the timing a particular weight. Then there were the particles, and these matter because they sit close to the central mystery. Around the arrival of the solar cloud, the energetic particle environment near Earth rose sharply. Higher energy electron flux at the altitude of geostationary satellites climbed to high levels, peaking near 2,874 particle flux units. That was beyond the threshold for an ongoing alert, and high enough to concern satellite operators, because spacecraft moving through such conditions can accumulate hazardous static charge. Proton flux, the heavier charged particles, did not cross the formal boundary for a radiation storm, but it was still elevated well above its quiet background level. Lower energy particle counts were also rising as the shock front from the cloud came in. In one measurement reported during live coverage of the event, a relevant proton reading increased from a quiet baseline of around 15 or 20 hundredths to roughly 1, a rise of several 100% while still remaining below the storm threshold. In simpler terms, the space around our planet had become more energized, more electrically active, and more crowded with incoming solar particles. This is the kind of detail that can sound technical at first, yet it helps define what Earth was moving through at that moment. It suggests an environment that was not calm, even if the larger meaning remains uncertain. To keep the discussion grounded, it is worth remembering how often geomagnetic storms already intersect with ordinary technology. The most dramatic historical example came more than a century and a half ago, when telegraph systems sparked, and in some cases their paper caught fire. A similar event in the modern world, dependent on satellites, electronics, and long electrical networks, could cause enormous harm to power grids and electronic systems over broad regions. More recent events have offered smaller but serious reminders. A storm decades ago brought down an entire regional power grid in well under 2 minutes, leaving millions without electricity in winter. Other storms have weakened satellite navigation, interfered with aviation routes over the poles, and even dragged newly launched satellites out of orbit before operators had time to respond. So when a strong geomagnetic storm is described as driving currents through the ground and through human infrastructure, that is not an imaginary danger added for suspense. It is a known vulnerability, one that grid engineers must account for. The sun's ability to affect technology is firmly established. The more subtle question, the one that gives this subject its quiet tension, is whether the same solar disturbance could also influence the ground itself in a way far harder to detect. So what is happening to Earth during a geomagnetic storm, if we strip away the jargon? When the solar cloud arrives and disturbs the magnetic field, it induces electrical currents. High above us, in the ionosphere, electrical currents move through the same region that helps kindle the aurora, the northern and southern lights. That upper atmospheric layer can also interfere with radio communication and weaken the navigation signals sent down from satellites. Yet for the question now coming into view, its most important role is quieter and stranger. Under the right conditions, it can help drive electric currents through the ground. This is not a fringe idea or a poetic image. It follows from established physics. When a magnetic field changes, electrical currents can be induced in conductive material beneath it. Earth's crust can conduct, and so can the long human-made pathways stretched across the surface, including power lines and pipelines. That is why severe geomagnetic storms are treated as real hazards to electrical grids, not merely as spectacular sky events. During such a storm, Earth is not simply a silent stone drifting through space. Its upper air and outer skin become electrically restless, disturbed by solar material arriving from far away. Hold on to that picture, because it is the foundation for the speculation we are moving toward. The essential point is not any single measurement by itself. The M9, the M7, the X-flare, the billion-ton cloud, the speed of 838 kilometers a second, the G2 storm behind, and the G3 storm ahead, the electron flux close to 2,900, the increasing proton counts, and the currents pushed into the ground all become important here for one reason above all: their timing. Taken alone, the sequence would have sounded like another active stretch of solar weather, the sort calm space often describes. It might have sent auroras somewhat farther south than usual, unsettled satellite operators, and given aurora watchers a memorable night beneath the sky. In fact, that was the story being told only the day before. Attention centered on the incoming cloud, the strong geomagnetic storm it was expected to produce, the possible glow on the horizon, and the practical question of whether electrical systems would ride through the event without trouble. A solar storm arriving as forecast was the headline. Then, beside that forecast storm, and on the very day it was expected to crest, another event entered the story. On the far side of the planet, the ground split open in the strongest earthquake of the year. We are left with two pieces placed side by side: an energized sun, storms on both sides of Earth's path through space, particles crossing 93 million miles, and a fractured seafloor during the same 48 hours. It is natural, perhaps unavoidable, to ask whether these events were connected. That question deserves care. A dramatic yes would be tempting, but it would overstate what can honestly be said. A quick no would be easier, but it might close the door before we have examined why the pattern feels so compelling. So we need to look in both directions, calmly, and with the evidence held in view. Part 5 brings us to the idea that the sun can shake the earth. Let us frame the claim in its strongest and fairest version before testing it, because this is exactly the kind of pattern that can pull the mind too quickly towards certainty. The proposal is not that solar storms create earthquakes from nothing. Precision matters here. No serious version of the idea requires the sun to summon a rupture in rock that carries no stored stress. Instead, the claim is about timing. Intense space weather, including storms and particle surges from the sun, may influence when a large earthquake occurs by nudging a fault that was already strained, already loaded, and already destined to fail at some point. In this view, the difference is not between earthquake and no earthquake, but between failure today and failure next month, or perhaps next year. That makes the hypothesis more specific, and therefore more interesting, than a loose feeling that distant events must somehow be linked. Researchers who argue for a connection describe a time offset, and that delay is the crucial feature. They are not claiming that particles arrive and the ground breaks in the same instant. Rather, the particle enhancement comes first. In their interpretation, Earth is electrically affected by the incoming flux of solar particles. Then, after roughly 24 hours, about a day, the statistical chance of a large earthquake appears to increase. It is a lag. The sun delivers its disturbance, and Earth's possible response follows later. Once that structure has been described, today's sequence becomes difficult to ignore. The particle flux rose during the day before the earthquake, and the earthquake followed roughly a day afterward. For someone who already accepts the one-day offset framework, this would look like the example they had been waiting for, almost the clean case they would choose to illustrate the idea. But a pattern, even a striking one, is not enough. What physical process could connect these two realms? Without a mechanism, correlation can be little more than coincidence wearing scientific clothing. To their credit, supporters of the hypothesis do offer mechanisms that can be discussed and tested. The main proposal is electromagnetic. As we have already seen, a strong geomagnetic storm can produce geomagnetically induced currents in the ground and disturb the planet's global electric circuit, the natural background movement of electrical energy through the atmosphere and Earth's surface. The argument is that a fault already pushed to the edge of failure, strained almost to the point of slipping after centuries of accumulating stress, might require only the smallest additional perturbation. In that scenario, the electromagnetic disturbance from a major storm could act as the final nudge, the last small straw placed on a system already near collapse. There is also a newer line of research involving what is called capacitive coupling. In that picture, the charged ionosphere above and the conductive ground below behave somewhat like the two plates of a capacitor, an electrical component that stores charge across a gap. Changes during a storm in this vast natural capacitor could, in principle, be translated into subtle stress changes deeper below. The idea remains something to examine rather than something to simply accept, but it gives the question a physical shape. And that shape is why the coincidence between charged skies and a breaking Earth can feel so difficult to set aside. What ties these proposals together is simple, and it is also the reason they can feel so persuasive. If a fault is already strained nearly to the limit, the argument says, it may not require much to let go. During an intense solar storm, the sun adds a small extra disturbance to the environment around Earth. Perhaps, in rare cases, that added disturbance could help choose the exact instant when a fault finally slips. It is an alluring idea, especially on a day when the pattern appears to arrange itself so neatly. The particle enhancement came before the earthquake, by roughly the interval the theory would expect. The quake sat between two geomagnetic storms, one before it and one after it. And the event was not a minor tremor easily lost in the record, but the largest earthquake of the entire year. As a single example, it almost seems custom-built for the solar earthquake hypothesis. If someone tried to imagine the cleanest possible case in its favor, the 48 hours that actually occurred would be difficult to improve upon. That does not make it proof, but it does make the moment hard to ignore. A careful mind can admit that the alignment is striking without surrendering to it, and that is where the quieter, more difficult half of the story begins. The prevailing view among most seismologists and space physicists remains skeptical, not because they refuse new ideas, but because the evidence has not yet cleared a very high bar. Their caution is not just institutional habit or a lack of imagination. It is based on serious physical and statistical objections that deserve the same attention as the tempting pattern itself. To begin with, no demonstrated physical mechanism has shown that the sun can reliably trigger earthquakes. The pathways suggested by proponents are possible to imagine, and they are not inherently ridiculous. Still, imagination is not enough. Even a strong geomagnetic storm carries energies that are tiny beside the immense stresses stored in a major fault zone. Stresses accumulated over centuries as tectonic plates move relentlessly against one another. The central problem is scale. How does a faint electromagnetic disturbance near the surface reach down to a fault kilometers deep and decide the timing of rupture? That bridge has not been convincingly built. The proposed push may be real, but it is extremely small, while the system it would need to influence is enormous. Until someone can show that the small effect can actually tip the vast one, the mechanism remains suggestive rather than established. This matters because nature often presents us with patterns that feel meaningful before they have been tested. The question is not whether the idea is interesting, it is whether it can survive the full weight of physics. There is an even deeper difficulty, and it is the one that must be kept in view whenever two dramatic events occur close together. Nearness in time is not the same as causation. That warning is not meant to drain the wonder from the story. It is simply how probability works. Earth produces large earthquakes on a regular basis. Magnitude 7 and above events occur many times every year, scattered across major faults and subduction zones around the globe. The sun, especially during an active phase of its one-year cycle, like the one we are living through, is also busy. Flares erupt, clouds of material are launched, and fast solar wind can buffet Earth. When two kinds of events both happen often, some of them will inevitably overlap on the calendar. They do not need to be connected for that to happen. With enough solar activity and enough earthquakes, coincidences are not rare accidents. They are expected outcomes. If researchers look backward after an earthquake and search for nearby solar disturbances, they will always be able to find some examples that line up. In a universe where solar storms had no influence on earthquakes at all, certain overlaps would still appear simply because both records contain many events and the year has a limited number of days. This is why broad studies matter so much. A single episode can look beautifully arranged, almost cinematic, but hundreds or thousands of cases tested with proper statistical controls tell us far more. The larger record is where a real signal has to separate itself from the background rhythm of chance, and that record is not simple. Some studies have reported statistical correlations at different levels of significance, and those findings should not be casually brushed aside. Others, using methods that are equally rigorous or even more demanding, have found no robust relationship once chance is properly accounted for. That mixed picture is important. It suggests that the question remains unsettled, but also that confidence should be limited. There is another uncomfortable detail as well. At least one high-profile recent great earthquake, a major event followed closely by many observers, gave a clear negative result. It happened when the sun was quiet and did not match the proposed solar trigger pattern. Any real theory has to face the cases that resist it, not only the ones that seem to glow in its favor. The solar trigger idea has such difficult cases. In science, the exceptions are not background noise to be wished away. They may be the very points that reveal whether a pattern is real. Another trap lies in how the evidence can be selected, often without anyone intending to mislead. Scientists call this a selection effect, and it can quietly create convincing-looking patterns from ordinary randomness. Imagine starting with the knowledge that an earthquake has already occurred. Then you choose which solar measurement to inspect. wind speed, particle density, proton flux, magnetic field angle, or one of many other variables, if the choice is made after the fact. And if any variable that appears to line up is allowed to count, then some relationship will almost always emerge. With enough options, chance itself can produce a result that looks meaningful. That is not the same as discovery. It is a form of fishing through the data, even when done sincerely. The crucial task is to distinguish a genuine signal from a pattern drawn after the event, like placing a target around an arrow that has already landed. That separation is what makes strong studies different from weak ones. It requires predefined tests, careful controls, and patience with results that may be less dramatic than a single, unforgettable coincidence. A powerful case study can bypass all of that difficulty because it feels complete on its own. Yet feeling complete is not the same as being complete. The honest conclusion, then, has to hold several truths at once. The correlation, in this case, is intriguing. The proposed mechanisms are physically conceivable, but they have not been proven. The timing is striking, but timing alone cannot carry the burden of causation. The wider evidence remains mixed, and the possibility of coincidence is not a minor objection. It is central to the entire question. A calm reading of the story leaves us neither dismissing the pattern nor embracing it too quickly. It leaves us watching carefully, asking what would be required for the idea to become more than a beautiful alignment in time. The prevailing scientific view remains cautious, and that caution is not rooted in dismissal or bias. It rests on a real methodological problem. One impressive alignment, even one as visually and emotionally compelling as the one before us today, cannot prove the existence of a hidden connection. In fact, under a chance explanation, unusual coincidences are expected to appear occasionally. What would matter is not a single dramatic example, but a broad, carefully tested pattern across hundreds of events, examined without cherry-picking, without searching endlessly until something seems to fit, and without drawing the bullseye after the arrow has landed. So far, that kind of decisive pattern has not been shown convincingly either for the idea or against it. This is what makes today's timing so absorbing, and also what makes it so easy to misread. The alignment may feel remarkable, while coincidence remains the default explanation that has not yet been defeated. Both of those statements can be true at the same time. If I have to say where I stand, it is here. We do not know. The responsibility to prove the case belongs to the claim, especially when the claim is extraordinary, and that burden has not yet been met. The fairest thing an intellectually careful person can say is that today offers a fascinating, almost unnervingly neat data point inside a question that is still open. Not settled in favor of a solar connection, not settled against it, simply open. There is something quietly humbling in that uncertainty. It asks us to pause at the edge of an unresolved question without forcing an answer, just to make the discomfort go away. And if the proposed solar earthquake link is one pattern the human mind is tempted to see in the noise, there is another pattern in today's data that may feel even stranger. To reach it, we have to turn our attention to the far side of the planet. Imagine starting at the earthquake's point of origin in the southern Philippines, then drawing an imaginary tunnel straight through Earth's molten interior and out through the opposite surface. That line would emerge near the middle of Brazil. The exact opposite point from any location on the globe is known as its antipode. Once that idea is in mind, today's numbers take on a curious shape. Before this magnitude 7.8 event, the previous largest significant earthquake had been a magnitude 6.9 near the Chile and Peru Trench in South America, and that site lies strikingly close to the antipode of the Philippines quake. Two of the largest recent earthquakes on Earth, appearing on nearly opposite sides of the world, can feel almost theatrical, as though the planet had been touched on one face and later answered on the other. But does that closeness mean anything? Or are we meeting the same coincidence trap again? only dressed in a new form? That is the question worth slowing down for, because the true physics is already remarkable without needing to overstate it. When a powerful earthquake occurs, Earth itself begins to ring. That is not just poetic language. It is close to literal. One of the most elegant truths in geophysics is that the planet has natural resonant frequencies, immense and very slow modes of vibration, rather like the tones of a bell or the faint response of a wine glass when a wet finger circles its rim. A sufficiently large earthquake can set the whole globe trembling in those deep oscillations. They are far too low and too vast for human hearing, yet they can persist for hours and sometimes even days after the obvious shaking at the surface has ended. This is not guesswork or mystical language. Sensitive instruments record it routinely after major earthquakes. For a time after a magnitude 7.8 or a magnitude 8, Earth behaves like a struck bell, quietly humming at frequencies no ear could hear. That image matters because it reminds us that a quake is not merely a local rupture. It is also an event that sends energy through the entire body of the planet. The waves, spreading away from the rupture, do not simply weaken in a smooth, even pattern, like ripples fading across a pond. They pass through the planet's interior, bend through layers of differing density and composition, and refract along their paths. As they move around the dense metallic core, some of that energy can reconverge on the far side of the world, gathering again near the antipode in a way that resembles light being bent and focused by a lens. When seismic waves focus like this, they can interfere constructively, meaning their energies add together. In some circumstances, that produces a detectable disturbance at the antipodal region, and it can even create apparent ghost arrivals on distant seismographs. Strange, delayed signals from waves that have traveled around or through the planet, and then concentrated at a remote focal point. So the notion that a major earthquake can reach across Earth and leave a measurable trace near its antipode is not fringe at all. The global ringing is real. The focusing of seismic waves is real. Far-field stress changes, meaning tiny shifts in the stress balance on faults far from the original rupture, are real as well, and they are studied by serious scientists. Up to this point, the picture rests within established mainstream Earth science. Yet this is exactly where caution must return, as firmly as it did when we were thinking about the Sunday. Two statements can sound almost alike and still mean profoundly different things. One says that Earth rings after a great earthquake, and that seismic energy can focus near the antipode. That statement is established. The other says that a great earthquake on one side of the world triggers another great earthquake on the opposite side. That second claim is far less secure. It is also precisely the kind of claim our minds may be unusually eager to accept. Human beings are pattern-seeking creatures, shaped by ancestors, for whom noticing movement in the grass could mean survival. Seeing a predator that was not there was a small cost. Failing to see one that was there could be fatal. In that sense, our minds may lean strongly toward connection, sometimes beautifully, sometimes misleadingly. It helps explain why we find faces in clouds, figures among the stars, and significance in coincidences. For science, that instinct is both a gift and a danger. It pushes us to ask questions, but it can also make a chance alignment feel like a message. On a world where powerful earthquakes are constantly being generated across the Pacific Ring of Fire and along the great fault systems of Earth, it is not difficult to locate dramatic-looking pairs. Some will appear close to one another's antipodes, just as some earthquakes will appear to fall near the timing of solar storms. The pairing itself is not proof. At most, it is a condition that would have to exist if a connection were real. By itself, it falls far short of demonstrating one. And this is where the deeper pattern of the night begins to reveal itself. From a single day, we are looking at two different arrangements with the same basic shape. The sun and an earthquake divided by roughly a day in time, and the Philippines and Chile divided in space by almost the full width of the planet. Each arrangement has the emotional force of significance. Each may even contain some small fragment of genuine physical meaning, because neither idea is automatically ridiculous. There are mechanisms worth considering, yet both patterns are laid over a planet that produces so many earthquakes, while also receiving so many solar storms, that convincing-looking coincidences are bound to appear, whether or not any hidden linkage exists. That is the real intellectual test of a day like this. The difficult part is not seeing patterns. The patterns are abundant, vivid, and almost impossible to ignore. The harder work, quieter and less glamorous, is separating patterns that reflect something real from patterns that are being completed inside our own minds before the evidence has caught up. This matters because curiosity and caution have to travel together. Without that balance, the night sky and the restless ground can begin to look like a single message, even when they may only be overlapping events. It is worth pausing on the appeal of the antipodal idea, because understanding why it feels persuasive can help protect us from being carried away by it. An antipode is geometrically clean. Earth is a sphere, and spheres invite symmetry. The thought that a violent rupture on one side of the planet might send some echo outward and strike the opposite point has a graceful, almost mythic quality, as though cause and effect had been drawn on the globe for us to see. It feels coherent. It feels like something nature ought to do. But that feeling of elegance is exactly where skepticism should become sharper, not softer. The universe is not required to arrange itself according to what the human mind finds neat, balanced, or beautiful. Reality is often uneven, disorderly, and unmoved by our preference for tidy shapes. When an explanation feels too perfect, too symmetrical, too satisfying, that may be the moment to examine it most carefully. Beauty can be one of the mind's most effective lures, encouraging belief before the proof has arrived. The antipodal pairing is beautiful, and for that reason it deserves more scrutiny, not less. And Earth offered even more material today for anyone tempted to weave every thread into one grand design. Around the time of the earthquake, the Pacific Ring of Fire was also showing widespread volcanic activity. In the Philippines, Mayon and Canalan were actively erupting. Across Indonesia, numerous volcanoes were venting and erupting, with plumes rising in several places. In Papua New Guinea, the largest ongoing eruption on the entire planet this year was continuing. Beneath the waves, a submarine eruption along a feature being called the Titan Ridge was still active as well. To someone already feeling that everything must be connected, this list can seem decisive. Solar storms, breaking ground, roaring volcanoes, all gathered into the same window of time. It is easy to feel the pull of that story. The question is whether the pull itself should be mistaken for evidence. A calmer explanation is not only available. In some ways, it is more compelling precisely because it does not need to reach beyond what is already known. The Ring of Fire is, in a broad geological sense, an interconnected system, a vast arc of subduction zones, faults, and volcanic belts surrounding the Pacific Ocean. It is under continual stress from the underlying motions of Earth's plates. So when earthquakes and volcanoes cluster around that margin, we do not need to invoke a cosmic alignment or a signal from the heavens. We may simply be seeing the expected behavior of an immense, stressed, interlocking machine whose parts are frequently active because the whole system is always being driven. Could the 7.8 earthquake have affected a nearby volcano that was already close to eruption, perhaps by shaking magma or altering pressure enough to speed degassing or eruptive activity? Yes, that is possible. Large earthquakes can disturb volcanic systems already poised at the edge, but they do not conjure eruptions from quiet, dormant volcanoes with no preparation, and much of the activity around the Ring of Fire was already in progress before today's earthquake occurred. The volcanoes were not awakened by the quake. They were already awake. That distinction may seem small, but it changes the entire story. It shifts the narrative away from sudden cosmic orchestration and back toward a planet that is continuously active, continuously strained, and continuously capable of producing overlapping drama. The more lasting lesson is subtle, and it reaches beyond this particular earthquake and this particular storm. The danger is not that we notice patterns. Pattern recognition is essential. It is the beginning of science. And every real discovery begins with someone seeing that two things may belong together and deciding to ask why. The danger comes when we stop at the noticing, when the excitement of an apparent connection is allowed to stand in for the harder task of testing it. A believer and a scientist can begin in exactly the same place. A pattern appears, the pulse quickens, and the mind senses possibility. What separates them is the next step. The believer treats the pattern as meaning and rests there. The scientist treats the pattern as a question and then begins the long effort of trying to disprove it, because only by surviving that pressure can an idea earn confidence. Tonight, with the sun and the earthquake, with the Philippines and Chile, we are standing at that fork in the road. We have seen the shapes. We have felt the temptation to connect them. Now, the only meaningful question is what kind of discipline we bring to what we have noticed. And that leads to the real center of the night, beneath the solar storm, beneath the sea floor, beneath the volcanoes themselves. The true battleground is the thin, shifting boundary between a pattern that belongs to the world and a pattern that has been assembled by the mind. This is one of the most difficult borders in science to cross with care, the border between uncertainty and suspicion. It is the place where reputations can rise, where careers can fracture, and where, if official answers seem too sterile or too incomplete, a darker story can begin to take root. So we arrive at the conspiracies, Part 7, why the numbers changed, and why that change frightened so many people. To understand the reaction, we need to return to something mentioned near the start: the magnitude. The first reports hovered around 8.1 and 8.2, close enough to megaquake language to make anyone watching feel their pulse quicken. Then, as the official assessment settled, the figure became 7.8. In seismology, that is not suspicious. It is the ordinary tightening of a measurement as better information comes in. Yet for many people following the event online as it unfolded, the same adjustment looked very different. It seemed to them as if the truth had been softened, as if someone inside an agency, somewhere out of view, had chosen to make the disaster sound smaller than it really was. That reaction should not be laughed away, not because the cover-up explanation is right. It is not, but because the impulse behind it tells us something important about trust and about how an open scientific question can sour into something far more corrosive when it is communicated poorly. The question becomes not only what the number means, but why people feel primed to doubt it. So let us slow the process down and describe what actually happens. When a major earthquake begins, the first magnitude estimate is produced automatically by computers using the earliest fragments of data from nearby seismometers, often within only minutes of the rupture. It has to happen quickly, because tsunami warnings depend on speed. If a wave may be moving toward a coastline, minutes are not abstract. They are precious, but speed comes with a cost. Those first values are not final verdicts. They are early glimpses, taken with limited information, while the event is still being understood. They can be messy, uneven, and incomplete, because the full seismic signal has not yet reached instruments across the globe. As time passes, more stations receive the waves. Computers and human specialists can then examine the broader waveform, meaning the detailed pattern of how the fault ruptured and how the energy traveled. The estimate is revised, refined, and corrected. This is the part that quietly undermines the conspiracy reading. The revision can go either way. At times, the final magnitude rises above the first estimate. In this case, it moved downward from 8.2 to 7.8. That is not a secret decision to reduce public alarm. It is the difference between a rushed image captured in darkness and a clearer image examined under steady light. The changing number is not a flaw in the system. It is one of the ways the system shows its work. In that sense, the revision may feel unsettling, but it is evidence of measurement becoming more accurate, not evidence of concealment. Still, the distrust itself deserves a serious answer rather than ridicule. Mocking people rarely changes what they believe, and in this case, the instinct comes from a recognizable place. It reaches beyond earthquake magnitudes into a broader fear that if something truly enormous were approaching, we would not be told. A catastrophic earthquake, an asteroid on a collision course with Earth, some event so large that officials, in this imagined version of events, would hide it to avoid panic, leaving the public uninformed for what they might call our own good. That concern should be answered plainly, not with blind reassurance and not with contempt. The strongest reason this kind of cover-up fails, for events like these, is not that everyone should simply trust the authorities. It is almost the reverse. The evidence is not sealed away in a private room controlled by a few officials. The people watching Earth and the sky form a vast, decentralized network, and much of that network is not under any single authority. Raw seismometer data from around the world can be viewed directly. Tsunami buoys report measurements close to real time, allowing water levels to be watched as they change. Solar telescopes provide continuous live images of the Sunday. Across every continent, thousands of amateur astronomers have the equipment to follow a large asteroid independently, and they would have no reason, no instruction, and often no desire to remain silent about a major discovery. For a detectable global-scale event to be hidden successfully, it would not be enough to silence one office or one government agency. One would have to suppress a sprawling, overlapping, international community of observers, many of them independent, many of them deeply motivated to be the first to notice and report something important. That is not a realistic picture of how information moves. The openness of the data is what weakens the cover-up claim. The fact that a person can look for themselves is precisely why the whole matter does not have to rest on faith. And this is where calm space draws a line that matters more than any single detail in the story. Fringe science and conspiracy are not the same thing, and treating them as identical is one of the quickest ways for curiosity to lose its footing. The disputed idea that space weather could have some influence on the timing of earthquakes, the possibility examined carefully from more than one side, is fringe science. It is marginal, uncertain, and unproven, but it is still a research question. There are peer-reviewed studies arguing in different directions. Possible physical mechanisms have been discussed, and the scientific debate has not vanished. A claim like that deserves an open mind held together with a strict demand for evidence. That is the proper posture toward fringe science. Neither worship nor dismissal, but patient testing. By contrast, the claim that authorities are intentionally lowering earthquake magnitudes or secretly hiding incoming catastrophes belongs to a different category. That is conspiracy. It requires a different response. Here is what is being alleged, and here is what the evidence shows. In this case, the claim breaks down as soon as we look at how observations actually circulate through the real world. One idea remains a difficult question that can be examined with care. The other is a story that cannot survive the open, decentralized nature of the data itself. The distinction may seem quiet, but it is essential. It may be the difference between genuine inquiry and a fear that only feeds on darkness. There is also a third idea that tends to appear whenever events like these crowd together in time. I want to acknowledge it plainly, and then leave it outside the door, because following it would undo the careful work this discussion has been trying to build. It is the claim that the earthquake, the volcanoes, the solar storm, and the arrangement of the planets overhead can be woven into one vast celestial warning sign, as if some particular pattern involving Venus, Jupiter, or any other planet could help set off a fault in the Philippines? That needs a firm answer. No credible physical process is known by which the visible positions of the planets in our sky can reach into Earth's crust and influence a fault system in that way. Their gravity exists, of course, but in this context it is so tiny as to be effectively overwhelmed by much stronger forces. The tides raised every day by the moon and the sun are already understood, measured, and included in our thinking. And they are thousands upon thousands of times more significant. Once earthquakes are tied to planetary alignments as omens, the discussion has stepped away from even fringe scientific speculation and entered astrology. Calm space is not going to take that path. The distinction matters, because the real question we have been circling is difficult enough without being buried under ideas that cannot support their own weight. The possible relationship between solar activity and earthquakes is worth examining precisely because it is different. It involves measurable particle fluxes, proposed physical pathways, and statistical studies that can be tested, challenged, and improved. Keeping that question separate from cosmic omen thinking is not a matter of being overly strict. It is a way of protecting the serious mystery from the kind of nonsense that can attach itself to it and discredit it by association. There is another instinct worth treating gently, and that is the impulse to suspect a cover-up. I do not think that impulse always comes from foolishness. Often it comes from fear. When something vast and alarming happens, something that reminds us how quickly ordinary safety can feel thin, the human mind searches for a form of control. It can feel strangely reassuring to imagine that someone, somewhere, has the full picture, but is hiding it, that the numbers are being shaped, that the story is being managed, that a secret hand is operating behind the curtain. In a painful way, that belief can seem easier to bear than the more unsettling possibility that no one is fully steering the system. The planet moves on its own timetable, and the people observing it, experts included, may be startled, uncertain, and learning as events unfold. A conspiracy can restore a false order to a universe that has just shown us disorder. That pull is understandable. But the more honest road, and perhaps the braver one, is to remain with real uncertainty instead of covering it with a story about hidden control. The truth offers less comfort than the conspiracy, but it is far richer. All of us, including the specialists, are standing on a world we only partly understand, watching the evidence together and adjusting our understanding as we go. And this is exactly why the legitimate question can be asked in the first place. The data are not locked away. We can examine the proton flux, the storm forecasts, the seismometer records, the tsunami buoy readings, and the solar images ourselves. That same openness is what weakens the cover-up narrative, and it is also what allows the solar timing question to be considered seriously, rather than accepted or rejected on belief alone. We are not forced to choose between gullibility and suspicion, between swallowing every cosmic story whole and waving away every real puzzle as meaningless noise. There is a better third path, to look slowly, carefully, with clear eyes and a grounded mind. So where does this leave us, near the end of the night? It leaves us facing a timing that still refuses to settle neatly, on a planet that never stops shifting beneath us. Part 8. A coupled planet. Now the lens needs to pull back, because after a day packed with striking pieces, it is easy to become trapped in the fragments and miss the shape of the whole. The larger view is steadier than the individual shocks, and, in its quiet way, more profound. The real picture is this. We live on a coupled planet. Earth is not a set of sealed, separate systems merely sharing the same address in space. It is a deeply connected machine, one in which the parts communicate through links that can be obvious, subtle, strong, weak, or still only partly mapped. Tectonic plates remain under continuous stress, locking, grinding, and releasing through a slow and enormous choreography. The sun is not a calm, unchanging lamp in the distance. It is an active, stormy, temperamental driver of the space environment surrounding our planet, sending light, particles, magnetic fields, and the solar wind across us every second of every day. The atmosphere, the oceans, the crust, the deep metallic interior, and the magnetic field that shields us are all part of the same larger story. Some connections are plain enough to see. Others are being painstakingly traced by scientists even now. The true scientific frontier is not whether Earth's systems connect. They do. The deeper challenge is sorting those connections by strength and reality. Which ones are powerful, which are faint, and which may exist mostly because our pattern-seeking minds wanted to find them. That is why the most useful thing we can do now is separate what is established from what remains open. This act of sorting may sound modest, but it is one of the strongest tools we have when the world feels noisy. On firm scientific ground, stress transfer between neighboring faults is real and well understood, and it is why we can expect the Philippine and Manila trenches to be carrying a little more strain tonight than they were yesterday. The free oscillations of the Earth after a great quake, the planet ringing like a bell, are also real and routinely measured. Geomagnetically induced currents moving through the ground and through power grids during a storm are real as well, thoroughly documented, and a genuine and growing engineering concern for the infrastructure that modern civilization depends on. What we can say with confidence is already extraordinary. The Ring of Fire is not a loose scatter of isolated danger zones, but a strained, connected system, with one part capable of influencing another through the familiar language of tectonic stress. Tsunamis, when they form, are controlled not simply by the size of an earthquake, but by how deep the rupture is and what kind of movement occurs along it. That is the solid reason the Philippines avoided the worst today, and why a heavily populated coastline is not facing a much darker count. These are not guesses or dramatic embellishments. They are the steady conclusions of established one-year science. And still, when we pause with them, there is something quietly astonishing in the fact that we understand even this much about a planet moving beneath our feet. The more uncertain thread is the one that has hovered over the entire discussion, like a faint light at the edge of the room, whether solar storms can, in any measurable way, influence the timing of earthquakes on Earth. That question has not been resolved for or against, and it would be wrong to force it into a neat answer simply because a neat answer feels satisfying. It belongs to that narrow and fascinating borderland in geophysics where measurements are possible, hints may appear, but proof remains difficult. Today gave us an unusually clean case to think about. A sun erupting repeatedly over several days, 2 geomagnetic storms, with one already behind the event and a stronger one forecast for the very day itself, and a particle enhancement rising through the day before the rupture in a way that almost uncannily resembles the one-day offset that supporters of the proposed connection often point to. Then, after that sequence, came the strongest earthquake of the entire year. Laid out in order, the pattern feels almost too orderly, as if nature had arranged the clues for us. Yet that is precisely where discipline matters most. When an alignment looks this elegant, the scientific response is not to surrender to the elegance. It is to slow down, to hold back from the easy thrill, and to admit 2 things at once. This is what a meaningful signal might look like, and it is also what coincidence could look like. At present, we cannot honestly separate those possibilities. Remaining inside that uncertainty is not a failure of courage or imagination. It may be the clearest form of intellectual care because it refuses to turn an open question into a false conclusion. There is, however, a broader idea worth lingering with, and it does not depend on the solar earthquake question being true. It is the idea of a coupled planet. For most of human experience, Earth and sky seemed like different kingdoms. The ground felt solid and enduring, the thing beneath us that defined stability. The sky seemed remote, a high realm of weather, lights, and powers beyond reach. Modern science has steadily worn away that separation. We now understand the atmosphere, the ocean, The crust, the magnetic field, and the sun, 93 million miles away, as parts of one continuous system, exchanging matter and energy in countless ways. A flare on the sun can disrupt a power grid in Canada. A volcano in Indonesia can cool the whole world for a year. Deep mantle motion, slow and hidden, ultimately helps drive earthquakes at the surface. The lesson is humbling. We do not inhabit a set of sealed layers stacked neatly on top of one another. We live within a restless, interacting machine, and even now we are still learning where all its gears connect. Seen from that perspective, the solar earthquake question is one possible chapter in a much larger story. Whatever its final answer becomes, it points toward the same unsettling realization. The boundary between sky and ground is not as absolute as it once appeared. It may be thinner, more permeable, and more complicated than earlier generations could have imagined. Whether it is thinner still in the specific way some researchers suspect remains uncertain. But the question itself reminds us how incomplete our map of planetary connection may be. So what should we expect next? Here the footing becomes much firmer because we return from speculation to established seismic behavior. Aftershocks in the Philippines should continue, with the largest most likely somewhere around magnitude 6.8, and they should gradually decline in both number and strength over the coming days and weeks, according to the familiar pattern of aftershock decay. The southern Philippines will likely remain active and uneasy for a time. Through the ordinary mechanism of stress transfer, near-term stress may be somewhat elevated along the neighboring Philippine and Manila trenches, which were already restless before today. Those are the places to watch most carefully, because the next significant regional event would most plausibly arise from that tectonic setting, not from anything overhead. The sun is still worth watching as well, though for a different reason. The active regions responsible for this week's barrage do not simply disappear overnight. They rotate, persist, and may continue to contribute to the present storm cycle before it calms. And for those willing to follow the stranger threads, with curiosity held in balance by skepticism, South America, near the antipode, may be worth a quiet glance. Not because the proposed alternating pattern has been proven, but because only patient observation across many events can show whether such a pattern deserves attention or dissolves under scrutiny. None of this requires believing that the sun shook the earth. It asks only that we keep looking at open data carefully, without rushing either toward belief or dismissal. That, more than any verdict, is the real lesson of a day like this. The event did not settle the question, and anyone claiming certainty is offering more than the evidence can support. Its value lies in practicing a rarer skill, holding two ideas together without letting either one fall. The timing is striking. Coincidence remains the null hypothesis, unless evidence truly defeats it. A mind that clings only to the first thought can start seeing cosmic messages in every overlap, every alignment, every accident of timing. A mind that clings only to the second can become rigid, brushing aside genuine mysteries as noise and missing discoveries that first appear as anomalies. The harder discipline, the one calm space returns to again and again, is to hold wonder and doubt in the same quiet moment, to be amazed by the alignment and skeptical of it at once. It is not an easy place for the mind to remain. We naturally reach for a verdict, for a clean explanation that lets the tension settle. Yet sometimes the most truthful ground is also the least comfortable one, and it may be better to stay there, uncertain but honest, than to accept a simpler answer that is not supported. So, at the edge of this story, one last question remains. It is not only a question about the Philippines, even though the suffering there tonight is real, immediate, and terrible. It is also a question about every one of us, and about the fragile world we have arranged beneath a restless sky. Part 9. The question that will not close. If we remove the layers of argument, The measurements, the timelines, the careful comparisons, what remains is stark. The strongest earthquake of the year happened during a solar storm. It followed several days of eruptions from the sun, came after a moderate geomagnetic storm 2 days earlier, and arrived after charged particles increased on the day before the rupture, echoing the one-day offset that some researchers argue should precede a major quake. At the same time, a strong storm had been forecast to reach Earth. And still, after all of that, the data cannot tell us whether the timing has meaning. Every instrument we have aimed toward the sky, every sensor we have placed in the ground, leaves us without a final answer. The question stands in front of us, and our hands are empty. That is worth pausing over, because the strangeness here is not mystical. It is not about omens, ghosts, or supernatural design. It is strange in a quieter and more modern way. After centuries of building the machinery of science, we still meet a boundary. We have satellites monitoring the sun through day and night, seismometers listening from the crust across the continents, solar telescopes, tsunami buoys, particle detectors, and supercomputers capable of searching for patterns in immense streams of information. This patient, powerful system has been turned toward one of the simplest questions a curious mind could ask. Did the event above us have anything to do with the event beneath us? For now, even this magnificent apparatus can only hesitate. It cannot settle the matter, and that hesitation from our strongest tools is the deeper unease at the heart of this story, deeper even than any single collapsed building. Though those collapses are heartbreakingly real, the fear is not simple, and it needs to be described carefully. Precision matters here, because fear can too easily become either panic or denial. The fear is not that the sun definitely shakes the earth. The honest conclusion remains that this has not been proven, and that the present weight of evidence does not support the dramatic, straightforward version of the story that sometimes circulates. That is not where the real disturbance lies. The more difficult fear is subtler. We live on a planet violent enough, beneath a star active enough, that we still cannot clearly distinguish a signal from a coincidence. With all our instruments, we cannot yet say whether the sky and the seafloor are exchanging influence in a language we have only partly learned to interpret, or whether we are simply creatures built to find patterns, watching two turbulent systems overlap by chance, because both are active in their own ways. That unresolved space is the unsettling part. While the question remains open, we continue constructing a vast civilization on a quiet assumption that the ground below and the sky above will mostly remain separate, mostly predictable, mostly willing to leave us undisturbed. We build power grids, satellite constellations, undersea cables, and bright cities of glass and steel, as if those two realms will keep to their own domains. Yet within the same 48 hours, on opposite sides of the same small planet, both seemed to refuse that calm expectation. Both reminded us, almost together, how limited our control truly is. Perhaps this uncertainty troubles us so deeply because humans are surprisingly able to live with dangers once they are understood. Even enormous hazards become more bearable when their shape is known. We understand that hurricanes gather over warm water. We can often see them forming, track their approach, and move people away from the path. We know that certain fault lines carry danger, and although our preparations are imperfect, we can design with that danger in mind. A known threat can be studied, named, and held in the mind. But a threat whose nature is unclear, where we cannot even say whether two events are linked, and where specialists themselves must answer with caution, reaches a more primitive nerve. It is the difference between seeing a predator in the open and hearing a movement in the darkness that might be an animal or might only be wind. The visible danger is frightening, but the ambiguous sound is harder for the imagination to release. In that sense, the solar earthquake question is a planetary-scale rustle in the dark. It is a possible connection that cannot be confirmed, yet cannot be dismissed with complete ease. That is why it lingers. Not because the danger has been shown to be vast, but because the uncertainty is basic, resistant, and still unresolved. So where does that leave us? One possibility is that it means nothing at all. Today may have been exactly what the cold mathematics of coincidence would allow. Two restless systems, each active in its own rhythm, briefly overlapping in a way that feels meaningful only because the human mind is built to notice alignments. Perhaps we are seeing a face in a cloud, as people always have. That thought may bring a little comfort, but it carries its own quiet unease. If the timing was pure coincidence, then the Philippines was simply due. The fault failed on its own severe schedule after a century of loading, and the solar timing was only a roll of cosmic dice that happened to look significant, a beautiful, meaningless accident. Or, with all the caution such a thought requires, perhaps we are seeing the faint edge of something real. Perhaps there is a genuine connection between the star and the world it warms, a connection visible only in statistics for now, not yet strong enough for certainty, and not yet earned as a claim. It could be a thread of cause and effect, too subtle for present proof, but not necessarily too subtle to exist. That possibility unsettles in the opposite direction, because it would suggest that the sun is not only the giver of light and warmth, not only the source of occasional satellite disruption, but perhaps a participant in the deeper machinery of the ground itself. It would mean there may be a hand on the planet that we have not yet learned to recognize. Both possibilities can trouble the night, each for a different reason, and perhaps that is where the story must rest for now. Not with an answer, but with the honest weight of a question still open. There is a form of bravery here that our culture may not honor often enough. We tend to praise the bravery of certainty, the firm belief, the sweeping declaration, the answer delivered without hesitation. Yet science often asks for another kind of strength, softer and more difficult, the ability to stand before a real, unknown, resist the temptation to force it into a tidy shape, and say, honestly, that we do not know, not as surrender, but as a commitment to keep looking. That is the discipline of real inquiry, and tonight, it is the discipline this story asks us to share. A simpler ending would be tempting. One version would say, with full confidence, that the sun shook the earth, leaving us startled and convinced. Another would dismiss the whole idea as nonsense, letting us feel safely reassured. But either conclusion would reach beyond what the evidence can carry. The more truthful ending is less comfortable, because it remains open. Still, an honest unease may be more valuable than a comforting illusion, because real understanding often begins in that uneasy place. False certainty, however soothing, can close the door too soon. What we can say is stark enough. The sky brightened, the seafloor split. These events unfolded on the same small world, within the same 48 hours, under the gaze of the instruments humanity has placed around it. And after all that watching, after all the measurements, all the careful science directed toward both moments at once, the most responsible statement may still be this: we observed them occurring side by side, but we do not yet know whether they were connected in any meaningful way. That uncertainty is not a weakness in the story. It is the honest center of it. There is a quiet dignity in saying we do not know, without rushing towards certainty in either direction. Perhaps the most important part is not the answer, but the act of watching itself. Real watching is not passive. It is a patient, almost radical refusal to look away simply because a question will not resolve. It would be easy to label the mystery unanswerable, set it aside, and let discomfort fade into forgetfulness. But the people who carry knowledge forward are usually the ones who remain with the unresolved thing, year after year, measurement after measurement, neither willing it into existence nor dismissing it before the evidence has had time to gather. That is the slow path by which genuine discoveries are made, And if the question of whether the sky and the ground are linked can be answered at all, it will likely not be settled by a single dramatic night, no matter how striking that night may be. It would be answered by many nights of careful attention, by repeated observations, by observers patient enough to hold the question open until the planet's own record becomes clearer. Tonight becomes one entry in that wider record. One data point has been added, and the ledger remains unfinished. The sun is not done with this moment. Those active regions still face our way, still capable, still charged with possibility. The aftershocks are not finished either. The ground in the Philippines is still adjusting and moving, while neighboring trenches remain loaded, waiting. Even the antipode, the far side of the world, has not yet offered whatever answer it may have. So we return to the only response that honest curiosity allows when a question refuses to close. We keep the instruments running. We keep both eyes open at once, the eye that is amazed and the eye that is skeptical. And we continue watching the sky, the ground, and that unsettling, unresolved electric space between them, where an answer, if one ever comes, may finally begin to emerge.